So this is the primary golden candidate for a Higgs production along with a Z, and both of them decay to jets. Well, they put all their events together, they tried to reconstruct the mass of that Higgs boson. These plots now show the combination of all the experiments and all the different decay channels that were observed, and going from here to there, ever tighter cuts on signal to background were made. And some people thought that there might be, this is the yellow is the expected background, the red is the expected signal for 115 GeV Higgs boson. And well, is there a signal or not? Is it just discovery of the Higgs, or is it just a fluctuation? So people were very excited because it did look like there might be some events, and there was a lot of argument about lab continuing to run so they could accumulate more data. But in the end, this reminds me of the little phrase that I long ago read in Louis Lyon's statistics book. The results of the experiment were inconclusive, so they had to use statistics. And statistics they used, and here's another way that the search for the Higgs boson has impacted the experimental particle physics program, because I think this is really the first time that experimenters were thinking very hard about how to estimate the significance of their observations. Do we see a signal? Is it significant? How do we do this? How do we estimate those? And so one thing, that method that was developed here, and I'm not going to go into tremendous detail on it, is called the CLS method, and it's still in use today. And these thoughts have continued, and this discussion have continued, and we have much more sophisticated methods today. But this is really where it started. So the conclusion of this was, well, it's not significant enough to claim that you see anything. On average, if you did LEP many times, you would, on average, be able to exclude a Higgs boson with a mass of 115 GeV or smaller. The actual exclusion based on the data was a little bit below, because there were a few events that were larger, in excess of what you might expect on average, but still, Higgs boson masses below 114 GeV are excluded at 95% confidence level by the LEP experiments. And a decision was taken to shut down LEP and disassemble the experiments and make space for the LHC. And so the Higgs search moved across the ocean to the Tevatron. And at the Tevatron, we thought we'd look for a lot of things, but we never thought we would look for the Higgs boson. Nevertheless, around that time then, the idea came up, well, can we see it? Since LEP didn't see it, there might be something. If it's at the mass that LEP saw that hint, could the Tevatron actually see it? And a Tevatron collides protons and antiprotons at a center of mass energy of 2 TeV. The luminosity, it's still the most luminous hadron collider in the world, is so large that right now it produces about 2 inverse femtobarn per year. The data that the Tevatron has right now analyzed is about 5 inverse femtobarn if it runs for another year or two. By the end of that, there might be 10 inverse femtobarn available for analysis. Now, there were studies done. What's the chance that the Higgs could be seen at the Tevatron? And we started dreaming about data sets of 30 inverse femtobarn and things like that. And if you could get that much data, you actually would have a chance of discovering the Higgs. So what this shows you is the integrated luminosity, the amount of data needed versus Higgs boson mass to exclude the Higgs boson at 95% confidence level if you don't see it, or to actually discover it with the 5 sigma statistical significance if you do see something. And so with 30 inverse femtobarn, you would be able to discover it all the way up to masses of 120 GeV and maybe here in this region. Or you would be able to exclude it over this entire mass range. So it seemed to be possible, and it was a strong push to actually get to the high integrated luminosity and do more than what was planned for run 2 of the Tevatron. So again, the Higgs was driving the program, the experimental program really at the Tevatron. And while in the end it turned out not to be practically feasible to quite get to that integrated luminosity, we seem to be able to get to 10 inverse femtobarn. So how is the Higgs produced at the tevatron? Sally has presented some of these already. It's gluon fusion is the dominant production mechanism with the biggest cross-section, and by far. And then at smaller cross-sections, you have production of the Higgs boson along with the W or Z boson, and then even smaller is like the boson fusion. Now, as I learned from Marcus's talk, there's lots of QCD background. So if I just use the gluon fusion, I have a Higgs in the detector and it decays at the mass that we're looking at. The Higgs decays to B jets, BB bar, and there's no chance of seeing that in the background at the tevatron. So you go to these production mechanisms where you got the Z and the W in addition to give you a tag and reduce this QCD background, and then you can look, you also see a Higgs boson in the event. So that's the strategy for the mass of the Higgs below about 130, 135 GeV, where it predominantly decays into BB bar. Now, once the Higgs boson mass becomes larger than that, the W pair decay will take over as a dominant decay mode, and then you can see the decay of the W pairs, which sticks much more out compared to the QCD background. You can actually take advantage of the gluon fusion production mode to look for the Higgs boson at that mass. So the search breaks down into two regimes: a low mass Higgs that primarily decays to BB bar, and a high mass Higgs that primarily decays to W pairs. Here's one example channel to show you a few distributions. So we produce a Higgs along with the W boson. The W boson decays to charged lepton plus the neutrino. The Higgs boson goes to BB bar. And here is plotted the dijet mass, the mass of these BB bar pair. So that's the Higgs mass. It's the Higgs decay that causes the events. So here's a spectrum of what you would expect to see. This white is W's produced along with jets. The red is just jets, and there's some other processes in here. And down here, at the bottom of the list, is WH, and you can't even see it here. So we need to do something to enhance the signal in that still humongous background. So what you do, you ask to identify these jets as B jets. That wasn't done here yet. So then we get significantly less events, because we throw everything away where these jets don't originate from B quarks, and a lot of that white background goes away. Now W plus heavy flavor plus B quark production, C quark production without a Higgs in between are the dominant events. And down here again, you see now WH, there's this Higgs signal, although it's enhanced by a factor of 10, so you'll be able to see it. So even after you ask for both of these jets to be identified as B jets,